ladies and gentlemen, we come now to our final presentation of the morning. Marcel.
So for the agenda today, at first I want to give you a brief description on how a trusted execution environment works and what it does. And after that, I want to go into technical detail on how to investigate in those. So let's start with the trusted execution environment and the general idea. So on the right side, you have an image showing a normal world and a secure world. So the idea behind the trusted execution environment basically is to separate the one world from the other world. So we have a strict line between them, and the normal world can't access the secure world directly, the memory and also the data in it. So for this talk, I will focus on the ARM TrustZone. There are different solutions for a trusted execution environment, but the ARM TrustZone works like this. You have one physical core that separates into two virtual cores, basically. So you have a secure configuration register, and one bit, when it flips, it will switch the context between the normal world and the secure world. Okay. So how does a normal world look like? Your typical operating system is running in a normal world, for example, like Windows, Linux, or some Android. We have different applications in here. So for example, some mobile games, some streaming service, and also trusted applications that are lying on your file system somewhere. So they are not in the secure world. Some of them are in the secure world, but not all of them. So when we want to work with a trustlet, we have to load it into our secure world in the trusted execution environment, and then we can work with this trustlet. For example, to give an application in the normal world some data. For example, if you're watching a stream on some service, you will get an encrypted data from the servers. The app would then send it to the trustlet. The trustlet would decrypt the data stream and then would send it back to the normal application. So one important point here is that the normal application in the normal world will never have access to the cryptographic key inside of the secure world. So it only has the encrypted and decrypted data stream. Okay. Like I said before, I'm an embedded penetration tester. So how to go from here and investigate in trusted execution environments? I like to set up a test environment first to look how everything works together. And that's exactly what we're doing right now. How to set one up is we can use some solution I found online, for example, Opti. I think it's a pretty good solution and implementation for a trusted execution environment because it has a good documentation, is quite simple to set up, and it also implements the global platform API specification. So this specification describes the API that is exposed to the trustlets and also describes how to communicate with the trusted execution environment, basically. That's good because this global platform specification has members reaching from Apple, Google to Cisco and so on. So we have a lot of vendors using them and a lot of big companies are also using them. So if you can research with that setup, you maybe also can use it for some different devices. That sounds good. And the last thing is it supports Cortex-A cores using ARM TrustZone. So we can use our cheap Raspberry Pi 3B Plus and connect it to a simple UART TTL adapter. And then over USB, we can talk from the notebook over our UART TTL adapter to our GPIO pins on the Raspberry Pi 3B Plus with our trusted execution environment. That sounds good. So let's imagine we got this device for a test and we want to investigate in this device, or more specific, the trusted execution environment of this. Therefore, we found some trustlets flying around on the file system, and now we want to examine them further. So if we got a trustlet on this device, it looks something like this. It has a signature. In it, it has some application code. And when it gets loaded to the trusted execution environment, it will also link to some libraries So for example, to map some memory or also access other trustlets in the trusted execution environment. And that's basically also why it's just flying around on the normal file system, because it has a signature. So we can't just manipulate it. That we changed something in the application code, it won't simply load the trustlet. Okay, so how to extract the application code for an OPT trustlet? It's pretty simple. We can use binwalk, for example. Binwalk is a tool to extract other file types in a single file. So if we use it on our trustlet, it looks like this. It has a UUID and then the ending trusted application, or in short, TA. And we can see that it has some ELF 64-bit file on the offset 0x148. So if we extract it, for example, with DD, we have just a raw ELF file and we can examine it further. Okay, so how does this application look? Simply said, we have some setup code. So for loading the trustlet and open the session. After that, we have our most important call, so the invoke command entry point. We would invoke it from the normal world. So for example, if we have our application that is requesting to decrypt or encrypt some stream, we would send it a command. We would land here, and then we would call the correct handler. So for this example and investigation, I simply implemented this trustlet myself for an example, and also implemented this command get key handler. And that is what we will see on the next slide. So we want to investigate here. Okay, so right now that we have the trustlet running, or the application code of the trustlet, we can reverse it with your favorite reverse engineering toolkit, for example, Ghidra. And that's exactly what you can see on the right side. So here we have the decompiled view of this single function. The most important parts of the function are the parameter types and the parameter themselves. So for the type, like the name says, we can get different types from the normal world. So we would load it up and then would get typical types like a value input, value output, value in output, or also the same for buffers. So a buffer input, buffer output, and buffer in output. The parameters themselves are containing the data. So here we would have, for example, if the parameter type would be in value in, we would have just 3, 4, 5, for example. It also could be some buffer. And the maximum parameters we can get are 4 at the same time. So 4 different values or 4 different buffers, or a mix between those two. Okay, so let's check what the function actually does. So here we check if we have the parameter type 3. And parameter type 3 says, because we have this global platform API specification, we can look it up. And that means we have a value in output. So we give the trustlet a value in output, and it would also return the value in the same parameter. After that, we would check if the parameter is less than 3. So, okay, that's good. We have a value, it's less than 3, and after that we would go into the single branches. So here, for example, we check if it's 1, we would get the public key number 1. Here we would check if it's 2, so we would get the public key number 2. And here we would check if it's 200. Okay, that seems strange, and we would get the private dev key. Okay, so that sounds interesting, but at first it looks like we can't reach this branch because we're checking here if it's smaller than 3, and after that we are checking if it's equal to 200. Okay, so that seems strange. Let's investigate further. So for me, the question is, how would we go from here? And the next thing that came to my mind was an emulation of this single function. And that's what we are doing right now with Killing. Killing is built on top of Unicorn, which is itself a CPU emulator, and killing takes some abstractions, so it can automatically load ELF files or handle some other operating system stuff. You can use simple Python scripts to use killing, and you will see it here. So at first we have to address the offsets from the beginning of the function to the end of the function. So it would look like this. The offset 0x13c would be the beginning of the function, and the offset 0x2ec would be the end of the function. Okay, the next step is to hook and implement all the functions that are getting called inside of the trusted execution environment. For example, here we have the traceprint function, which would call code inside of the trusted execution environment. And because we don't have access to this trusted execution environment, because it's a gray or black box approach, we would have to hook it and implement it in our Python code emulator. So here we would get the parameter 0, or in our register x0, and the parameter, the next string in x4. So we would print out getKey. GetKey has been called in this example. After that, we simply put it in, print it out in our Python console, and then we directly return out of the function so that we are not calling any instructions whatsoever for this function. After that, we obviously need some setup code. Like I said before, we need the parameter types and some registers. We need a buffer, so where the actual parameters are lying. Then we need some space in this buffer and also our parameter inside of the buffer. So here we would use the 0x1. So later, if we are trying to execute our emulator, we should end up in this branch. And the last thing we do is some verbose output. So for example, if you want to know where we are in the current function, we can print the program counter. I skipped it on the next slide where you can see the output of this short emulation. And then we need to set it up. So basically that's our main. We hook our print trace function at this offset. We hook our setup function, and then we just run it from the beginning to the ending of the function. Okay, so let's execute it and see what it prints. So here we have it. It will use the profile linuxql because it's an ELF 64-bit file. Then we load it to some base address and so on. And here we get our print from the setup function. And we also see that we are getting to this point because it's printing out the traceprint function. And then we're getting here to the public get key number 1. So that sounds good because it seems like our emulation is working. The question is still, how can we get here to this branch? So instead of manually trying to enumerate and test different inputs for this value, we could use a fuzzer to automatically change the values for the input and try to get here. And that's what we are doing now. We are using AFL++. It's a black box fuzzer we can use, and for that we can use this to find a vulnerability. For us it would be the branch 200. The good thing is that AFL++ has also support for killing or also for unicorn, so it has support for the emulation part. That's good because we can just retake our previous file for the emulator, change some things, but mostly it will be the same. So here, again, you can see we're just loading it up in our killing, give it the correct trustlet with the extracted ELF file. Then we would have a function with the input bytes we are getting from the fuzzer. So instead of directly giving it like a correct value of 1, 2, 3, or so on, we would just give it this input parameter that it permutates on each call. After that, we have to start AFL, of course, give it this input file and also our place input callback. And for the last part, we also have to hook up the addresses. So basically we have for our trace function and to start AFL, but the most important hook here is the callback for the 200 branch. So to find this branch, we have to say to AFL that it should stop executing or that it should crash when we are reaching this 200 branch. And that's exactly what we are doing in this line. We say that if we are ever reaching this 200 branch, we should abort, and that would cause a crash, basically. So a crash for us is that we're getting into this branch. So let's execute this code and see what it outputs. So here we can see the actual output of the American fuzzy lob. We have the process timing, so like how long is it running? We have some cycle process, some stage process, what it is trying to do. And the most important part is here on the right side, we have the unique crash and also here findings in depth. So we have a crash, and like I said before, that crash could be related to executing or going into our 200 branch. Okay, so that sounds interesting. So let's see the output of AFL and check what the input was to the trustlet. So here we can see that the input was C8. So let's try it in our own manual emulator and change the byte from 0x1 for the first branch to C8 and see what happens. So right here, you can see again the setup function, and the only thing we have to change is the buffer, the bytes that are in the buffer, and that bytes are C8. Okay, so let's run this and see what the output is. All right, again, we have like our profile, we have our base address, we have our setup print, and then we can see here we are getting into this branch for the developer key. Okay, so that is interesting. Where to go from here? Like before, I said we set up a test environment, so let's test it also on the bare metal device. That should be our device under test. So it would look something like this. And for that case, I also implemented some normal world app that is called Hacktivity Showcase to load and execute something, to load and execute the trustlet. So it will give some command ID to the trustlet and the actual parameter, which is in this case 51,400, and it is equal to 0xC8. So that should work, and we should get it into our 200 branch. So here we can see it is loading this trustlet. It's also getting to this create entry point, and that's where the interesting stuff begins, because we can see the first print from the trustlet. So it calls, or it says hello Hacktivity. Then it invokes some things, get key has been called, and then we are ending up into this private developer key branch. Okay, so the last thing we want to know is why is it like this and why we are getting to our 200 branch. So it turns out that it is a simple C cast mistake, because at first we are using the value or the parameter as an int16 to check if it's smaller than 3. And after that, we are using it as an unsigned integer 8. So we have a difference between those two. If we calculate it, we have the C8 is 51,400, 51,400 modulus 256, because we have 256 different values for an unsigned integer. We're getting the 200, and that's why we are also getting into our branch. So further steps would involve, if you want to investigate further or have deeper functions, you have to improve the fuzzing speed, and you could also use symbolic execution, for example, to mathematically solve this problem. There are even more possibilities to investigate in those, but I won't cover those in this talk. So thank you for listening. Here are the sources I used for this, and have a good day. Bye.
Thanks for that, Marcel. I'm just going to take any questions, if you just give us a moment, please. Are there any questions from the audience for Marcel regarding his presentation? There aren't any questions at this time, Marcel, and I have not seen any online as yet.
All right, so let's summarize this talk in a few sentences, maybe again. So I would say trust execution environments are here to create another layer of security. And because they encapsulate the normal world from the secure world, and the keys are stored and also the data is stored inside of the trusted execution environment. So that's one important part. Some trustlets are loaded from the normal world and can be examined but secured with the signature, and there's also encryption for them, but I haven't covered this in that talk. And for the emulation and fuzzing part and so on, it is not as complicated as a few years ago, because it was at the start. And you can see that only one page of Python code is needed to do crazy stuff like emulating and fuzzing this trustlet. So that's really great, I think. It's therefore easier to get into this topic, and the problems come with a more complex functionality, so deeper nested functionality and also functions you can't easily emulate. And it also comes with optimization of the fuzzing or emulation part, and that will eat a lot of your time. So if you're interested, just download the tools on the last slide and have fun playing around with them. You can also reach and text me on the Discord, on the official Discord of Hacktivity, so I can answer your questions. So have a nice day and thank you for listening.
Many thanks, Marcel.